Okay, we got, let me see. Oh,
Hey, Walter.
hi. So everybody's here. Excuse me, not everybody's here. I'm going to I'm going to pause okay, this session is being recorded. So we welcome for today's presentation Dr. Elgohary from UCF. He's going to talk about cislunar satellites um, and the research he's been doing. And so I'm going to let him share the screen and start the presentation. Um, and so take it away, Eric. I mean, Eric, Tarek. Sorry.
No problem. Thank you. Thank you so much, Walter, for the invitation, and thanks for the AIAA at Central Florida for hosting this event. I know it's late and people are probably anxious to go home and have dinner and and relax. So hopefully this is not going to be too boring. A little bit about me. I am an associate professor at the Mechanical and Aerospace Engineering Department here at UCF. My main area of research is astrodynamics, space flight mechanics, focusing more on space domain awareness, either in Earth orbits or cislunar space, which is becoming the new frontier now in terms of space domain awareness applications. Um, Today, I'll be focusing on sort of a multi-threaded, multi-pronged research project that I've been working on for the past few years that is related to a how can we monitor space objects in the cislunar domain, and how can we do the various operations, space domain awareness operations in the cislunar domain. And I'll show you a quick outline, but a little bit about, see, all right, a little bit about my lab. So I manage, or I'm the director of the Astrodynamics Space and Robotics Lab, ASRL. In the top right here, you see we have a logo. Actually, this logo came to be, or came to existence just a few days ago. I've been the director of this lab for almost 8 years now, and finally we came up with a logo about 8 years into it. So there we go. So we do a few things in my lab. We do astrodynamics, we do space, more science related research, and we do robotics, which is kind of an overarching word for guidance, control, dynamics, and robotics. So, let's see. For astrodynamics, obviously, we're interested in debris, space domain awareness applications. For the space, we're looking at dynamics of lunar dust. More recently, we're awarded a grant from NASA to look into passive lunar dust mitigation, and I'm doing the modeling and simulation of that problem. I'm not going to talk about this here, but that's also one of the areas I'm doing research in at UCF. And finally, the guidance and control and dynamics related to re-entry dynamics for large type containers. We're doing the trajectory design control for that problem. And we have a robotics platform to run some of our guidance and control algorithms in the lab, trying to emulate space motion. This is the robot here downstairs. And I guess the main, or the the connection, the cement that keeps all of this together and keeps me sane is that this is all in the nonlinear dynamics, control theory, and computational methods type regime, which is my main area of research with, as you see, various applications. So what I'm going to talk about today is this idea of a cislunar optimal, or space surveillance optimal adaptive network, a CS-PAN for short. And if you look at the top right here, you can see that cislunar space is quite large. In terms of scale, where you can see here from Earth to GEO, the geostationary orbit, that's one. So distance in georadii, you could see that the cislunar space spans a very, very large space beyond that, a very, very large space beyond what we consider the boundary of Earth orbits, which is the geostationary orbit or the boundary of the Earth sphere of influence. And that space is of interest. In terms of kilometers, you could see that it is about 36,000 kilometers from the center of the Earth to or the surface of the Earth to the geostationary orbits. And the distance between L1, the moon, and moon L2 is about 61,000 kilometers. So in terms of scale and magnitude, cislunar space is quite huge. And in response to that, the Space Force, Air Force have proposed several missions. One of them is called Oracle to do space domain awareness in cislunar space. It's a space-based solution because due to the distances and the vast volume that requires coverage, Earth-based observers or ground stations will not be the best approach, will not be able to give you the coverage you need. So we have to rely on space-based assets to monitor that space. There's a lot of interesting orbits that come out. This is a chaotic system. As a dynamical system, it's chaotic. A lot of interesting things can happen. A lot of free transfer orbits can happen. I'll show you a couple later on. So it has a lot of challenges in terms of surveillance and understanding what's going on there. So our research, and this is sort of the three legged thing that we're working on here is that we're looking at this network from a multi-observer, multi-target model that essentially does triangulation in a sense. The other part of it is how we quantify coverage in that space. What are the tools, the fundamental research tools that we can come up with to quantify coverage, essentially volumetric coverage in the cislunar domain, and how we can do this rapidly and efficiently so that it transfers to tasking and optimization. And I'll talk a little bit about that. And then finally, how we can rapidly compute uncertainty. So as you see, we will have this Oracle or CHIPS mission. It used to be called CHIPS, but they changed it to Oracle. CHIPS stands for Cislunar Highway Patrol System, but they found that the name is a little bit too much, so they went to Oracle. So the idea is if you're gonna do this on space-based surveillance type spacecraft, then you need or we need a way to quantify uncertainty, make predictions in a rapid and real time on board, and that's the third component of that research. So if we look here down here, this is sort of how we link those things together. We have the multi-observer, multi-target framework. It needs to handle heterogeneous sensors, asynchronous measurements, error estimates based on coverage and geometry. So it needs to be able to figure that out. This feeds into the coverage models where we need to quantify coverage, understand multiplicities of coverage, and include constraints. Those two things work together that gives us metrics for performance and fast or real-time computation. So metrics for performance then is used to tasking and optimization of the network. So essentially answering the question of where to place these things in to meet certain mission objectives. And if we place them and there is new information, how can we task or retask them in real time or as close to real time as possible. So that's sort of how it all fits together. Uh, all right. So this is where the fun starts. Basically, our idea of a multi-observer, multi-target observation model is very simplistic. It comes from a very fundamental result that two planes construct a line and two lines construct a point. Or the intersection, I mean, of two planes and the intersection of two lines. So if you can see here, we can come up with planes based on line of sight, basically camera measurements, so angles only measurements. So we have here that cartoon, which shows obviously not to scale, but shows observer one, observer two, or observer one, observer two, target one, target two. We have line of sight from one to two, from two to two, and the same thing. Now, the difference here, the main difference here I want to highlight in this construction is that observer one and observer two are not connected. They do not know their location relative to each other. They are trying to estimate their position and the target position by just looking at the targets. So usually in these problems, you will have a map and the agents in the map know or have means to know where they are relative to each other, and this helps in that convergence scheme. But this one, it's only looking at targets. The other thing is we're doing this in an inertial frame. In this sense, the inertial frame is the rotating frame or the synodic frame, which is attached to the Earth and the Moon, and the whole system is rotating in this cislunar domain. So that's essentially how we construct the normals, which defines the planes, and that's how we can construct the measurement model, which has the normal for target one, of observer one, plane one, and so on. So you can essentially start concatenating all of these things and collecting them together. And here, this is the what we need to find, which is the target minus the observer, and then we can decompose this as I'm gonna show later. Uh, One of the main things that you can use this for, something called initial orbit determination. So we want to, this essentially AX equals B, that's a simple least squares type problem. We take the time derivative of that to include angular rates. And essentially what we get is that we come up with the position and the velocity of the target, essentially a full initial orbit determination using least squares. So this is all a function of these normals coming up from angles only measurements and the position and velocities of the observers. Now, for initial orbit determination, even though we can introduce uncertainty in the observer's location, for the initial orbit determination problem, we assume that they are deterministic. And again, the initial orbit determination problem is a very rough, you can call it like the back of the envelope solution for the orbit problem. And then you feed that into either a batch estimator like a nonlinear least squares estimator or a sequential estimator like a Kalman filter as an initial guess, and you take this forward. Okay, so this shows how we get, and I'm not gonna go deep into the math, but this shows how we essentially come up with the various normal planes, so and their derivatives, and essentially it all comes down to the angular rates and the angles of coming from the observer. So it's an angular problem, and the angular rates we can do an interpolation because you get those as streaks, if you will. And it becomes a least squares problem where we can solve for the x dot, the velocity and position of the target, given the 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 line of sight, the angular rates, and line of sight and line of sight dot function of the normals, all the planes, and the locations of the known target, the known observers. So quickly, this case, this is only an initial orbit determination case. Essentially, we have observers in the DRO, a DRO orbit. So in this cartoon, you see this is the moon, very tiny. This is the DRO orbit. We have an observer here in the DRO orbit. We have an observer on the surface of the moon, and we are looking at a 9-2 NRHO, N 9-2 N NRHO, a non a rectilinear, near rectilinear halo orbit target. So here we're doing IUD with two measurements, three measurements, four measurements, and so on. This case for IUD has been shown to diverge previously in the literature. And with this method, we were able to come this is log in meters and log in meters per second. So we are talking about centimeter error in cislunar space. Now, centimeter error, and I won't go back very quickly in this scale. The inertial frame is somewhere here. This is where the point. So in that scale, we're talking about orders of meter or centimeter error in distances that spans tens of thousands of kilometers. So percent error, we don't show percent error here because it will look ridiculous. It will look like, 10 to the minus 6 something, which we don't want to do that.
Hey,
So,
Tarek, may I ask a question?
hey, Yunjin, I
Hey,
did not know you
yeah,
were here. Yes, go
hi.
ahead.
Yeah, I'm interested in your topic.
Thank you.
I'm curious. Looks like you are in a three-body problem, or
That's circular restricted, yes.
okay. So is that dynamics included in this estimation, or just the geometry information right
That's IUD. No, no dynamics. Dynamics will come later.
now? Okay.
So that's initial orbit determination. So Gauss, like Gauss, like Laplace, right? Like
It's
you take three
basically
measurements,
only
you do kinematics.
yeah, it's basically only geometry, right?
Yes, so the solution here, if you look at the components of this the least squares problem, you
Hmm.
see there are only angles and angular rates, so
Yeah, yeah.
no accelerations.
Okay, okay. Thank
Yeah,
you.
yeah, yeah. So that's IUD, no accelerations. It's just kinematics, and we're getting with kinematic, and here I'm highlighting its kinematics. Oops, I went ahead. This is kinematics. With kinematics, we're getting about meter error in scales that spans 10,000s of kilometers. Cool. All right. So what we did is obviously we went to the next step where we looked at, and this is one of the very interesting orbits in cislunar space, where we uh, this orbit is called the 2-1 retrograde resonant orbit. So this orbit is very interesting because this is let me see. This is Earth. This is Geo. Like this red orbit is geostationary. And that is the 2-1 retrograde orbit. You could see that it goes from Geo all the way to the basically the all it goes by L4 and L5. These are the libration point, the Lagrangian libration point, and it essentially arrives at a DRO orbit, a distant retrograde orbit. So essentially goes all the way to the moon, essentially in a sense. So that's a free transfer that you can go from Geo all the way to all the way, and this is an example of the DRO orbit up there. It's sort of perpendicular to that plane, but you can go all the way to the moon on a free transfer, or very close to the moon on a free transfer. And these are the kinds of orbits that are very challenging to monitor because you're not thrusting, there's no thrust, there's no fuel being spent. You can just start there and do the whole thing and arrive at DRO. And then when you're in DRO, you can essentially come and land on the moon. So those are this case study we did with using an EKF, an extended Kalman filter, and the idea is we use this idea of several observers looking at the target on this path to DRO, and here we have a few observers in GEO, a couple of observers in L4, a couple of observers in L5, and then a couple of observers in around the moon in DRO. And you could see here that this orbit comes and crosses very close to the moon. So this tiny thing is the moon. Okay, so it basically can arrive to the moon very easily, and we have observers in DRO like this, the orbit that you show here. And you can see the Kalman filter performance here, where you have some measurements in GEO, and then the Kalman filter is the bounds are diverging because you're not getting any measurements, you're just propagating uncertainty. And then you pick up measurements again, and they diverge again in this maybe in L4 and this region, no measurements, and then you pick them up again, and so on. And same thing for velocity. So this is the position error, the velocity error. And here we show the entry and exit of each region where we have observers. So you can see here that And also we did, I'll show you this here. This is for the case that we have, which is delta t equals 2 minutes. But so here we have a position error of about 300 meters in geo. And then we exit geo with 200 or about 300 meters error. And then we enter L4 with about 8 kilometers error because we're propagating the uncertainties. Now we acquire measurements, so the error comes down, and then we increase the error, reduce the error, and you can see how the error is moving up as we're not acquiring measurements and being controlled with this method. The idea here, or what we're trying to show here, is the convergence happens very, very fast once you start acquiring measurements, and this is enabled by that measurement model. And we did study on how far the measurements could be while we are having custody of the object. So 30 seconds, 2 minutes, 10 minutes, 20 minutes. At 30 minutes, it diverges. The EKF doesn't really work. You can go to an unscented Kalman filter in that case.
Well,
But
Tarek, do you think you say initially it's okay, but later on start to diverge? Do you think it might be because your numerical integrator issue? Because
no, this is the divergence due to the frequency of the measurements.
oh, okay.
So while you're having measurements, so you see, you don't have measurements at all the time. This is not full custody. So you're losing custody and then acquiring it, and then losing it and acquiring it. And while we're having custody, we started experimenting with the frequency of measurements. So starting from 30 seconds all the way to 30 minutes, and we found that the threshold is about 20 minutes, and it works around 20 minutes. Beyond that,
Oh,
the
yes, I
filter
look at wrong
diverges.
place. Yeah, I look at wrong place.
Okay,
I'm surprised that your errors are so small,
me too.
your position errors.
Yeah. So that and I think what I'm trying to show here is how well that measurement model can bring down the error very quickly versus the current state of the art. Um, All right, let's see if we can go. And this is the case where we did everything. So this is a case where we have multiple observers in DRO, a distant retrograde orbit, tracking multiple targets in 9-2. So we have and we go from 1 to 5 and 1 to 4, or 2 to 5, 1 to 4. So obviously for this to work, the minimum number of observers looking at one target has to be 2 because we're using these intersection of planes. So 2, 3, 4, 5 observers, 1, 2, 3, 4 targets. And here, this is an orbit determination. So that's nonlinear least squares. So here we have the dynamics involved as well as, but we're not doing a filter. We're not doing a sequential for this one estimation. So what we have here is 2 targets looking at one object, 2 targets looking at 2 targets, sorry, 2 observers and 2 targets, and so on. And you can see in most cases, in all cases, essentially, the solution improves as you increase the number of targets, the number of objects, the number of observers, and the number of targets. The accuracy improves. So this is RMS error. I think we did this over a 1,000 Monte Carlo simulation. So this is the averaging of all of this type of exercise. And it makes sense because you're getting more measurements, and as they acquire more measurements, even if they are not looking at each other, the observers, the overall accuracy improves of everything in the process. So here we have 5 targets looking at 5 observers looking at 4 targets. You get essentially the best results. Essentially, you're introducing more measurements in the system. But the idea is, here we're showing that you can actually estimate both the observers and the targets simultaneously by just looking at the targets without having knowledge of where the observers were. There is uncertainty on the observer's location and uncertainty in the target's location, which is more realistic when you have space-based observers. Because obviously on ground stations, you know where they are on Earth. They are not going to be perturbed. There is no uncertainty of where they are. So you assume they are deterministic. The only uncertainty is in the target, the spacecraft. But here, because everything is space-based, so you have uncertainty in both. So we're showing that this actually works very well when you have multiple targets, multiple observers, both everything with uncertainty. Cool. All right. So that's sort of the first part related to the multi-observer, multi-target. The second part is on the volumetric coverage. So how can we quantify coverage? And the coverage problem has been very, very interesting in the space domain in general. So uh, attempts have been done before, mostly planar type ideas, assuming directional sensors. It was very, very fundamental. And there has been several publications in that. Some people tried a little bit more complex algorithms to define coverage using some sort of finite element for volumetric coverage, but it suffers from runtime issues, computational complexity. Uh, what we are looking at here is something that we adopted from more of computer science type ideas, and they are essentially called octrees or orthrees in n dimension. So if you look at this cube, that's an octree, so a three-dimensional representation of a volume, and then you can start dividing that cube into more cubes. And then each one of those cubes, you can divide them more into more cubes. So it's sort of a tree structure. This is sort of the quad tree representation, the 2D or the 1D representation that one becomes eight and so on. So parent-child representation. And this way, we can represent this sphere, if you look at this cartoon here, with various levels of fidelity. I don't know if it shows, but you have like smaller squares and larger squares depending on the how far you go down the tree structure. So what this it looks like is essentially there's a lot of stuff here, but I'm gonna use that example, which is a quad tree. The quad tree is the two-dimensional representation of the orth tree, which is the general n-dimensional representation. So what you see here is if I want to represent this circle in this structure, this quad tree structure, so I will have full cells with these addresses. So these addresses are the cell addresses and partial cells, which we can go even further and divide them even more. So for example, this cell here is fully covered. And then the next one, which is so it goes in the next level, this is like the bit representation. So it's more it's more on how you represent these cells in a bitwise representation. Then you have those two cells as a higher level quad tree, and then you have those partial cells that covers that structure or that covers that circle in the plane. And we do this in 3D for space domain awareness. What you see here is this is called the Z curve or the Morton curve, and essentially you move. This is the cell, the first one representation, the second one, and here, like for example, 0.9 here is represented by that bit structure, and so on. So this is how you represent the addresses of that. So this is the higher level quad tree. It has that bit structure, so that represents that cell. And then you go further down, this becomes this guy, which is, you know, that the next level from here. So you can represent it with the bit structure. So that's the very general idea of octrees and orthrees. Now, octrees are 3D, orthrees are n-dimensional, and quad trees, which I used here for demonstration, are two-dimensional. Let's see. Okay, so combining that with constructive solid geometry, essentially what we're trying to do, so looking at that could be your sensor profile, for example, that could be the area or the volume you want to cover, and that's the intersection. That's what actually your sensor will see in that out of that volume. Okay, so we can, and you can see here the structure of the, in this case, octrees, because they are three-dimensional. And you can see here that if you want to capture these edges, we go further down the fidelity or the resolution until we capture all these edges and represent that shape. So constructive solid geometry essentially becomes intersection, union, containment type operations where we use them to find what a sensor profile, when a specific sensor profile intersects with the space that we want to cover, it gives us what the sensor can actually look at. So we can also do multiplicities of coverage. I'm not going to go into all the details here, but the idea is to find the how many if you have overlap, how many of those can you represent? You can come up with the address. So this is if you look at the bottom right here, you have a multiplicity of one, a multiplicity of two, a multiplicity of three. So and they are shaded. So multiplicities of one, these are the areas that are only seen once or by one sensor. Multiplicities of two and three are by two and three, and so on. So that's how we can also come up with a way to represent multiplicities. And the important thing here is that this whole representation using the Morton curve or the Z curve, it becomes just a one-dimensional interval, a 1D search. So this is not computationally complex at all. And actually, I'm going to show you the computational complexity of this in next. So these are more on doing the operations. So essentially the starting and stopping point with the cells. So this is the starting, the stopping point. Essentially how you can algorithmically represent those in your code, right? So I'm gonna quickly skip this. This is what I wanted to show. This is a quadratic complexity with the octree. So currently, if you're doing any of these coverage simulations, it's a cubic complexity. So it's n to the cubed. Here we are showing quadratic complexity as a function of the octree level. So you can see that you could show that it jumps quadratically as you increase the level, and this table actually represents this quite well. All right. Here we brought one of the cases that I showed in the very first slide, one of the geometric cases. So let me talk to you a little bit about how this works, because it's sort of a lot of geometry here. So on the right-hand side, you can see this is a sensor essentially looking at a dual band problem. So we call this the dual band coverage problem. You define a lower band and an upper band, and the sensor is essentially you're trying to quantify coverage between those two bands given a sensor profile. This problem assumes an omnidirectional sensor, so it looks everywhere at the same time. Again, non-realistic, but this is what the analytical methods can do. And these are all the parameters for this simulation. It came from one of the seminal papers in this area, and we regenerated the results just to show that we agree with the analytical solution. Now, what I want to show you here is even something more interesting than just agreeing with what the analytical solution does, because if we don't, then the whole thing is wrong. So obviously we did come up with using our numerical approach or the computational approach, we did agree with the analytical solution, but here is a level 3 octree. So we go from, we go 3 levels down the octree, and here's a level 6 octree. And what I want to show is that the solution always provides an upper and lower bound. Those upper and lower bounds, they shrink as you increase the fidelity, but the red one is the analytical solution, and this jagged line is the octree solution. And this enables you to do a very quick computation with a lower fidelity, and you're guaranteed to be within an upper and lower bound. This is very important if you are trying to do some tasking or some optimization very quickly versus trying to capture or nail down the actual coverage. So always having an upper and lower bound on the solution is very desirable, and you can always design your constellation or design your or task your sensors based on that knowledge versus going to 3 levels down, which increases quadratically, as I have shown. The complexity increases quadratically, but you get a very fine, very accurate solution out of that. So you have the control on how far you want to go down that resolution, and at the same time you get an upper and lower bound, so you cannot exceed that. Your error will not exceed that up plus minus, and that is very useful when you're trying to do something very quickly. And the average almost always conforms with the true solution. All right. So the last component, and I'm running over. Sorry, guys. I thought it would be 40 minutes, but it's not. So the last component is uncertainty quantification. So for that, we're using a lot of techniques, and our aim is always getting a way to do this very rapidly in the most efficient way possible. And I'm gonna skip a little bit of the math. This shows the basis functions that we use for approximation, the uncertainty approximation or uncertainty propagation. But I'm gonna show you the steps. So here we are using radial basis functions for to approximate the uncertainty. And here we're adopting sort of a two or a series of steps. The first one is we go for an approximation that is more high fidelity. And from that, I'm going to show that we use machine learning techniques to come up with a much faster sort of reduced order model, if you will. So here we have the initial uncertainty. We populate the space with RBF nodes. Here we use the dynamics and Liouville's theorem, which states that the PDF values, the probability values, if you are on a conservative or Hamiltonian system, stays constant. And if it's not, if it has drag or thrust, we have scaling methods to deal with that. Then we propagate forward in time. We populate uh, our domain with RBF nodes, and I'm going to talk a little bit about this. And then we optimize the RBF approximation and come up with an ND approximation of the probability density function. And then we do integrations to do probability of collision and so on, and then come up with a marginal PDF or a cumulative integral. Now here, this is the phase two, is once we have all of that, we can perform probability of collisions and so on, and that would be done, or it's being developed as we speak. So this is all the steps explained, and I'm going to skip a lot of that for the sake of time. But I'm going to highlight a couple of things that one is RBFs are very versatile. We don't have to stick to a certain nodal distribution. So if anyone is familiar with Gauss quadrature, you have to stick to some Gauss nodes like Lobato or Legendre or any combination thereof. Here we can even use random nodes. And here we chose Halton nodes, which are actually, they are semi-random for coverage. This is one technique that we are using that really you could see that here we have points in a normal distribution, and essentially what we have is adding a little bit of a boundary beyond that to create support. So we're doing a lot of approximation tricks to get better approximation for the support. Here I'm showing how we populate. So this is called the banana-shaped probability distribution. This is one of the most annoying things you can deal with if you're doing uncertainty propagation, because as you see, you want to capture the uncertainties. You want to capture the values at this very tiny tail of the distribution, and it's very hard to put points there. What we're showing is that with this technique, you can essentially capture all of that structure, as you see here with this extended boundary. So I'm here using a simple 2D problem, a Duffing oscillator, a nonlinear Duffing oscillator, just to show this in 2D, because the orbit problem is we cannot show all of that for the orbit problem. because the minimum you get is a planar problem and it's four-dimensional. So you cannot represent those things in a meaningful way in 4D. You cannot draw things in 4D, unfortunately. Here we show that here is what we are looking at in terms of the PDF at time 0. And you can see here what we're using is the log. So these are all the tricks we're using for this. So this is a log transformation of the PDF values. PDF values are generally very small. You can see all of them are very tiny here, almost 0. And then you have a few that are very high that represents the mean of that distribution. And if you want to do the approximation here, you again you get a lot of points at almost at 0, and then very few at this value. And here you see this is a much nicer, much more normalized distribution. So your approximation, your numerical approach will perform a lot better if you use the log versus the actual true values. And again, it's very simple to come back and forth from this. Again, this what we're showing here is now we're doing we remove these extra nodes beyond the boundary. So that's how we do like sort of a filtering scheme, and we remove all the extra nodes so we get the actual true values of the approximation. All right, so let me quickly so all of this is applied to this problem. It's Cislunar. Again, we're dealing with Cislunar. So a Cislunar orbit in I think it's around L4, I believe. Yeah, I think it's an L4 type orbit. Here you can see what we have here. We have the initial boundary and the initial distribution, the final distribution. So here, this tiny speck here is the initial distribution, and it goes through. This is a very small portion of that orbit, and here we get the final distribution. One of the metrics we use here is to show that the cumulative integral of this whole thing is 1, which it should be. So we compare this with the Monte Carlo simulations. Now, what I want to highlight here is we can see that if we use a baseline, a Monte Carlo simulation of about 5 million samples, and we have 1 million sample, we're getting about between 12 and 3x improvement. And this is high fidelity. So we're not losing any information here. This is a way to do high fidelity in a much more efficient way. Now, obviously, with anything, you still have what is known as the curse of dimensionality. So this is an approximation technique. The dimensionality increases, the computational burden increases exponentially, essentially. So for that, now we look at machine learning, transfer learning, how we can use the high fidelity that we just learned or we just came up with to train, and then if we have a new object or a new RSO resident space object, we transfer the knowledge and essentially come up with an uncertainty quantification solution in a much shorter time and with a lot less computational effort. For this, we came up with what is known as the structured state space models in machine learning, also called Mamba. And the idea is these structured space-based models or space-based models in some cases, they have state space representation in them. So AX plus BU, which we like and are familiar with. So we have tried so many things, and I'll show you a few attempts later on here. So this is for this, we're testing propagation. What you see here is a cislunar orbit. Here we have PINs, which is a physics-informed neural network, shallow feed-forward, LSTM with self-attention, and Mamba. And this is all the computational complexity that come with all training with all training and network representation. This is a stable halo orbit in L1. We propagate this for 5 orbital period. This all was done on a nano, Jetson Nano. So all of this is done on very low computational power hardware. that is essentially space flight qualified. So the thing is we want to highlight here is this is the decimal accuracy between pins, LSTM, Mambas, but I think the main thing in here is the parameters. So the pins use 48,000 parameters, LSTM use about 20,000 parameters, and we're using about 1,000 parameters. Again, the memory usage is several orders of magnitude, couple of orders of magnitude less in using Mamba. So this is why we think this would be a very, very good tool for uncertainty quantification on board spacecraft technique. Now, we experimented this further with low data scenarios. So essentially, we trained in two epochs, the initial conditions and then something that happened, I think, 6 minutes later or something like that. And we compared our solution with LSTM, Mamba and LSTM. Again, I'm jumping ahead, but Mamba is used generally in large language models, and LSTM is essentially a technique that is used in machine learning for, it's called long short term memory, and that is used for time series data. So, for example, something that learns handwriting that uses something like LSTM. And obviously, Mamba is in large language models like ChatGPT or something like that. Okay. So you see here what we have here is a low data scenario. Obviously, LSTMs is like this is so far off. It doesn't come close. This is the true orbit. And that's the LSTM solution with self-attention. Only training on 2 points is never enough. But this is the Mamba solution, only training on 2 points. Again, we didn't expect it to be 100% accurate, but that's pretty good for only training on 2 points. So we're also exploring that for training for space domain awareness type applications. We're also looking at explainability. That's very important in machine learning, how we can explain how the network is behaving. We're trying to see there is an approach called the superweight approach. Essentially, we're trying to figure out if, for example, the state space model or the state space portion of the network is essentially maybe taking care of all the linear terms, and then the nonlinear terms are taken care of by the convolution layer. So we're looking at explainability, and we came across the super weight approach. It assigns there's a way to come up with weights on the various portions of the network, and we're still testing this, but that's one area where we try to connect all of this. Why does it work so well, and how we can make predictions on it in the future. Now, this is how we link it to, and this is a very quick cartoon. This is how we link it to propagation of uncertainty. Here, this is our PDF approximation, very simple. This is the coefficients of the PDF approximation, the RBF coefficients that I mentioned earlier. We assume that this is, as we go forward in time, we make the assumption that the uncertainty or the coefficients are time varying. Okay. So, and here we learn from the high fidelity approximation, and we use the techniques I showed earlier to learn the new coefficients as a function of time. We published a paper more recently on this, got a best paper award using that technique in a conference. So we're working on a journal paper for that technique, but I'm just showing this as a very, very high level um, uh, uh, extension at this point, but we've already published some results on that. And that's it. I hope I didn't take too much of your time. Thank you so much for listening, and I'll be happy to answer any questions.
Thank you very much, Tarek. Appreciate
Thank you.
that. Everybody give him a round of applause.
Thank you.
Good job, Tarek.
And so I'd like to start maybe with one question. Does this methodology have applicability to other orbits? And I'm thinking about like asteroid, say if you're trying to minimize the error in around not cislunar, but cis asteroid space.
Yeah, you can.
I'm thinking
The dynamics are you can feed in any dynamics into that. Obviously, we haven't dealt with chaotic behavior, although we played with chaotic behavior in the Lorentz attractor, for example. We use Mamba to predict Lorentz, and it worked very, very well. This is in our paper, but yes, the short answer is yes, but the devil lies in the details.
Understand.
Yeah,
Thank you.
yeah.
And,
I-
does anybody have questions? Go ahead.
Yeah, I just have a quick one. I just wanted to confirm for myself that these sensors are radar sensors or
Optical.
optical sensors.
Yeah.
Okay.
So they're getting in that sense, you're getting two angles from the sensor.
Okay.
Azimuth, elevation, right, ascension, declination, those kinds of angles.
Okay, but purely optical? I mean, you're not adding any other type of modality.
In the we started with optical because they are the most challenging. Because optical sensors, you don't get you don't have range information, so you have ambiguity on how far things are. You essentially get two angles on a sheet of paper, right?
Right, right.
Yeah. So the idea is you use many of them to disambiguate how far things are. Essentially, it's like your stereo camera idea, right? Like you're with two eyes, you get depth. With one eye alone, you generally it's very hard to get depth.
Right. So you've got the parallax and
Yeah.
you
Yeah.
can
So you get many of them
triangulate.
to resolve that ambiguity in depth. And but if we in the matrix that I showed very earlier, where you have these blocks diagonals, you could add range, you could add range rates, you could add angles, angular rates, so range rates comes from Doppler. Range, you can have any like LiDAR or radar or type of applications. So
Right.
yes, you can integrate all of that into that big matrix and add as many sensors as you want.
Okay. All right.
Yeah,
Thank you. Yeah.
sure.
Any more questions?
And Walter, how do we get a copy of the video taken
Oh,
tonight?
I'm going to
What
send a
slide?
copy to everyone that is in the audience. Are all of you AIAA members or?
I am.
Yes.
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 Okay, so I'm going to send this recording out to the membership.
Okay.
If you're not an AIAA member, then you might not be on my distribution list. Would you please send me an email to walter.e.hammond@gmail.com.
All right.
Any more questions?
Yeah, I can ask questions when I see him, but I'm very interested to see what's the difference between LSTM and Mamba. It's just Mamba is a linear function.
Yeah, so I didn't go much into this. I don't even have the structure of an LSTM. So the LSTM structure so this is the Mamba structure. Okay, let's
Actually,
start
this is
with this.
very
So you have,
similar to LSTM.
I'm sorry?
This is kind of pretty similar to LSTM,
Yes, but in the LSTM, you will have you don't have the state space basis. You don't have
It's
that
more like
layer.
it's more like some
It,
kind of nonlinear function
it's
for
a 10 like a 10 function, and then it
and
has
all the loose
it
stuff.
has yeah, and it has some gates, so
Mm,
it keeps the memory on one and move forward, and then can delete the memory from that gate. It has that structure, right?
mm,
But this one is a little bit different because it has the state space and it has a convolution layer,
mm.
and essentially that's your feedback, and then there's a linear projection for this. Sorry, I'm using my finger. This one, these are linear layers.
Yeah, that's very strange. It looks like you know, it- yeah, it looks like similar to CRNN, also similar to LSTM.
Mhm.
Um, but
Yeah, there are obviously some similarity. The feedback structure and so on. It's essentially so LSTM is a component of RNN, right? Like a recurrent neural network. So
one
it has
type,
a
yeah, one,
feedback. Yeah,
one type.
yeah.
So this Mamba only works for linear system, is that right?
No,
Or
no, no.
mm,
Actually, it works. I have results for Lorentz attractor. Like it predicted chaos.
uh,
So it's actually very it's too good sometimes.
uh, so PyTorch right now has a Mamba package as well because I know LSTM is there.
Yes, I believe it does. Yes,
Mm,
this is my what my student is using.
mm.
Yeah. So definitely check it out. And yeah, we definitely, if you want to talk about it, we can, because it's very interesting. And it's not used at all in our communities yet, because it comes from language models, natural language models, large language models.
Yeah, but I'm curious why in larger language model they use this state space form because they don't have any formally defined equations there.
Yeah. Yeah, I agree. It's very interesting, but the idea was they wanted to avoid the LSTM, because the LSTM requires a lot of data.
Mm.
So they wanted something, and I don't know how, to be honest, I don't know how they came up with it, what made them come up with this structure. The paper was published, I want to say, and I will send it to you. As they publish all of these things, it's on archive, and it was published December 2024, like or late, like yeah, it was published.
2024, it means like just 2 months ago?
No, sorry, December 2023. If
Oh, okay.
Yeah, so about a year ago, and it exploded since then. And we've
Mm,
been using it. I think we came across it in February or something,
mm,
when
mm.
we came across it
Yeah.
last.
Typically, this is the reason that people right now are curious about how, develop something which can be easily explained, right? Because most of
Yep.
this machine learning model, they don't have an easy way to explain why. We
Yes.
just know it works.
Yes, and that's why we're very interested. That's why we picked it up, because we saw that structure and we said, okay, we have a state space model. We can do something with it.
Mm,
If we can capture it. But to be honest, it's not turning out as
mm,
easy as we thought
mm,
to define explainability or interpretability. But
mm.
we're working on it, because we're trying to figure out what part of the system that does that state space capture.
Yeah. You also mentioned about the used LSTM plus some attention
Yeah,
strategy.
self-attention. Yeah.
I To me, LSTM already won't have one step attention already, right? Because it's time sequence stuff.
Mhm.
So what do you mean, attention in your LSTM? You add extra, looping it, or you put
Yes,
you put some
yes. So
weights somewhere?
so you can implement LSTM without self-attention, right?
Mm,
So using the same structure, but with self-attention, you add another loop to it. Yes.
mm.
And there is a paper also in that community. It's called "All You Need Is Attention" or something like that.
That's for ChatGPT, right?
Yeah. Yeah. So that's where LSTM with self-attention came across.
Is this LSTM with self-attention also the packages available? Because I used LSTM quite a lot, but I didn't notice there is a self-attention package there.
I don't know. Let me ask my student then
Oh,
about if self-attention is something he implemented or something that was readily available for him.
oh, okay.
Yeah, I'm not 100% sure about the self-attention component.
Mhm. Okay, cool. That's very interesting.
Yeah, thank you.
And I haven't been to this type of conference for many years.
hmm
Is machine learning become very popular there?
So this conference was very machine learning. This is called the Dynamics Data Driven
Oh, okay. I
System.
see. I was
Yeah,
thinking
so
that the different conference.
no, not our Astro conference, but now it's getting very, very popular using machine learning. So there are several sessions that has machine learning in
Mm,
Astro now.
mm,
It wasn't like that a few
mm,
years ago.
mm.
Okay. We got time for one last question. Going once, going twice. I wanted to thank you very much, Tarek, and
Thank
people can
you.
follow up with Tarek for further questions and so on.
Cool.
Thank you very much.
Thank
I'm
you.
gonna
Thank you.
end the call now, and I'm gonna stop the recording.